All right, if I could have your attention, please. Good afternoon, everybody. My name is Don Brenner. I'm the department head here in Material Science and Engineering. Welcome. Thank you for coming. We appreciate this, and it looks like a very full house. In addition to our distinguished speaker today, this is also part of our 100-year celebration. So we are now one of the certainly the oldest materials program in the Southeast and one of the oldest materials programs throughout the nation. And so we're celebrating all that with alumni coming back and distinguished talks and other things. So thank you for joining us with that, and I appreciate that. I want to acknowledge one person today, and so this is the Robert Davis Distinguished Lecture, and I want to acknowledge Bob and thank him for his support of this series. All right, so let me pass this over to Professor Sitar, who will introduce today's speaker.
Okay. Yeah, hello everyone. It's nice to see everyone in a relatively big number, as much as auditorium can take, I guess. It's my pleasure to introduce today's speaker, Professor Hiroshi Amano of Nagoya University. He's a 2014 Nobel laureate, and he got the Nobel Prize with two other Japanese researchers, Professor Nakamura, who is currently at UC Santa Barbara, and Professor Akasaki, who was also at Nagoya University, and Professor Amano's actually mentors. So the citation from the Nobel Prize was like, for the invention of efficient blue light emitting diodes, which have enabled bright and energy saving white light sources. So this sounds like very exciting, and that you have a gadget that you can actually hold in your hands. But the reality or the importance of the work that had been done at Nagoya University at the time is pretty basic in material science. So let me point that work out. The main problem in gallium nitride at that time was that it grew in two polarities. So it had nitrogen polar and gallium polar domains, and one was highly conducting, so which basically disabled any real device fabrication. So, and Professor Amano actually developed a process that that enabled the growth of one single polarity layers, and that was really the prerequisite that enabled then p-doping of this material. And once the p-doping was done, then it was easy to make the device. So I think the citation from the Nobel Prize Committee sounds a little simplistic, but the background is very rich in the material science as we have it. And since we are celebrating 100 years of material science department, we can actually somehow sense how important it is to understand materials and actually be able to manage them to achieve the properties that you actually want. And Professor Amano today is going to talk really about the future of gallium nitride and what the dream is for this technology. So please, Professor Amano.
Thank you.
Thank you, Professor Jita, for the kind introduction. Good afternoon, everyone. I'm Hiroshi Amano. Congratulations on the 100 years of this department establishment. And also, it is my great honor to be here and give a talk as the Professor Robert Davis's lecture series. So, my presentation is the wide and ultra wide bandgap semiconductors. I know that the North Carolina State University is the place that most active in this field. And today, there are many young researchers. So I'd like to send a young researchers, and also I'd like to show some our activities on this materials science, which Professor Zitter explained. Okay. If I remember correctly, Professor Davis visited our university 30 years ago, right? I'm sorry, I couldn't remember the exact date, but in the late 1980s or the early 1990s, and showed us an extremely high temperature operation of silicon carbide FETs. It was 500 centigrade. Wow. It's great. So we followed his work using not silicon carbide, but the gallium nitride. Maybe it's liable materials. So as Professor Jita mentioned, we concentrated on the nitrides, especially the gallium nitride. But at that time, in the 1980s, we are very, very poor. So I'd like to explain first why the poor Japanese university, our university, sparked the blue LED revolution. This is because of the late professor, my mentor when I was a student, his strong commitment to his original LEDs. So let me explain the Professor Akasaki's first. He was born in Kagoshima. It was Kyushu district, and when he was the primary school student, there was the World War II. So there was a very serious attack occurred in his life. And then after that, he entered the Kyoto University. The major was the chemical science. And then after graduating the Kyoto University, he joined Kobe Kogyo in 1952. And there was a famous researchers, Dr. Reo Esaki. He also received the Nobel Prize in Physics in 1974. And at that time, the TV broadcasting service started. So Mr. Akasaki, his research was the development of phosphors for brown tube TVs. And he was strongly fascinated with the luminescence phenomena. Phosphors emit light without heat. Okay. Then Mr. Akasaki moved to Nagoya University in 1959. And he was devoted to crystal growth of germanium by vapor phase epitaxy. At that time, the semiconductor was not a silicon. The semiconductor was germanium. So through this experience, Mr. Akasaki learned that interdisciplinary research, Professor Arizumi, his major was electronics, and Akasaki's major was chemistry or materials. So the combination of these two research fields explores the new research areas. And also, he needs to prepare key materials, that is germanium single crystals. Okay. Then, after getting the PhD, he moved to Matsushita, now Panasonic. And then he met with the LEDs, red and green LEDs. The manufacturing was so successful, so he got the award of the president. But he had to comply with the patents owned by the US companies. So he was pursuing his originality. That's why he started researching blue LEDs. Then he started the blue LEDs by gallium nitride in 1974 using the molecular beam epitaxy. At that time, it was more than 50 years ago. So MB technology was still in the very, very preliminary stage. So according to his subordinate, Dr. Toyoda, when Dr. Akasaki said he would start gallium nitride research by molecular beam epitaxy, Dr. Toyoda thought Dr. Akasaki has lost his mind. But over the many, many objectives of those around him, Dr. Akasaki started growing gallium nitride by MB. And his team could not succeed in fabricating blue LEDs by MB. So he changed the growth method from MB to HVP, halogen transport vapor phase epitaxy. And his team succeeded to fabricate MIS type, metal insulator semiconductor type, not the PN junction type blue LEDs. But his group have to use the patent owned by the US companies. So Matsushita managers decided to cancel the blue LED project and suggested him to start long wavelengths optical communication laser diode. So therefore he gave up on the company and moved to Nagoya University in 1981. At that time, almost all the industry players around the world had abandoned gallium nitride-based blue LEDs and started working on zinc selenide, another rival materials. Then at that time, the rival materials was zinc selenide, silicon carbide, and then gallium nitride. Okay, so he said, I walked around in the wilderness. So I met the research topic that motivated me best is the gallium nitride-based blue LED. I was an undergraduate student. When I saw the theme of graduation research, gallium nitride-based blue LEDs for undergraduate student, I thought that is it. Because if I could achieve blue LEDs, I could realize flat panel display like you are using now, that I could change the world. Yeah, at that time, all the displays are the cathode light tube. It was very big, and the consuming electricity is huge. So I can use it as the heater. Okay. Yeah, Professor Akasaki tried the original technology for growing gallium nitride, so he decided to start the new growth method, that is metal organic vapor phase epitaxy. But at that time, Akasaki laboratory was very, very poor. It was only US dollar 20,000 per year. And there are many students, more than 15 students. So if we divide it, I could use only 1,000 or something. So the students developed our own MOVP reactor using a second-hand spare parts. To realize the good or high efficient blue LEDs, we need three important achievement. Okay, so the high quality crystals, N-type and P-type, and the luminescent materials in indium gallium nitride. So at that time, no one succeeded to grow high quality crystals. So I have to start with trying to grow the high quality crystals. During the undergraduate and first and second year of master course, almost 3 years, I concentrated on trying to grow high quality crystals. I had experience 364 days per year without the January 1st. Okay. I have almost every day trying to grow high quality crystals, maybe 3 to 5 times a day. However, I couldn't realize the high quality crystals. But in such a desperate situation, I enjoyed to repeat the experiments. The experiments I did from my first year to third year of undergraduate were not fun. Because they were made by research assistant, young researchers, and I knew the results before I did experiments. But this time, we made our own MOVP reactor. We developed our own reactors and were able to think about the experiment on my own. I have never had such an enjoyable experience, so I could concentrate on performing the experiments. So at that time, I was very, very enthusiastic. And then I faced my turning point to enter the doctoral course. In August 1984, Professor Akasaki recommended me to enter the doctoral course. Although I could not succeed in growing high-quality gallium nitride crystals for almost 2 years, I was so enthusiastic in growing gallium nitride crystals. Therefore, I decided to enter the doctoral course at the end of August. However, in September, the trouble happened in my family. Therefore, I lost the financial support from them. But I was very, very lucky that I was able to obtain a scholarship from the Japan Scholarship Foundation by the support of Nagoya University, so I could enter the doctoral course. So I decided I'll try my life differently than everyone else. Okay. If I had completed my master's degree and entered the workforce, I would spend a lot of time comparing myself to others. However, I was able to get on go on to doctoral course program so I could live in this way, a life when I can pursue what I want to do. Then, at the end of the master's course, I finally succeeded to grow high-quality gallium nitride crystals. At that time, I planned to deposit aluminum nitride before growing gallium nitride. The aluminum nitride research had been done by Mr. Koide, who was 1 year my senior. And his aluminum nitride had flatter surface than my gallium nitride. So to grow aluminum nitride, I knew that I had to grow it at a higher temperature than gallium nitride. But there was trouble in the heating system. Yeah, we used a very, very old heating system. So the gross furnace was in a bad shape, so I couldn't reach the temperature required for aluminum nitride. But I decided to enter the doctoral course, which means that I have to write journal papers. Okay. At least 3 journal papers necessary to get a PhD. So I was in a hurry and deposited aluminum nitride first, even at low temperature. And then, when the growth was finished and the wafer was taken out of the growth furnace, the surface was the cleanest I had ever seen. So I thought, oh, I forgot to pour out the raw materials. But I checked to make sure that I did not have made a mistake. So I looked at it under the microscope and found that almost perfectly flat gallium nitride had grown. I was moved beyond words. So I wrote the journal papers, and it was easily accepted. I think it is because at that time, no one had conducted the gallium nitride research. So maybe even the reviewer did not understand what's happened. So my paper did not take any notice of other researchers. But for me, it didn't matter that others were not interested in gallium nitride. My motivation is to get the PhD. So I had to publish 3 journal papers to obtain a Doctor of Engineering. So I began the challenge to realize P-type gallium nitride, next challenge. But it is silicon carbide. Silicon carbide was so successful to obtain both P-type and N-type. But at that time, the gallium nitride, we couldn't get the P-type gallium nitride. The reason is thought to be a self-compensation. The self-compensation means that this is the gallium nitride crystal structure, and if we replace gallium to zinc. Zinc is the Coulomb-2 element, so the valence electron is 1 electron is missing. So the zinc capture electron from the valence band and then give a hole to the valence band. So we can get the P-type gallium nitride. But if we replace gallium to zinc, the nitrogen vacancy automatically forms, which have which gives the electrons to the conduction band. Therefore, this electron and this hole compensate each other and could not get the p-type gallium nitride. That was the concept of self-compensation. Okay? I couldn't accept such an idea because I realized the world's highest quality gallium nitride. So I should realize the p-type gallium nitride. So I've experienced a lot, but still I couldn't do it. So the doctoral course, the 3 years of doctoral course was so stressful to me. The mood in the laboratory at that time, I should make a blue LEDs with conventional MIS type, not a PN junction, and write a paper on it, and then go out. However, the library material, zinc selenide, there had been a lot of p-type reports. And also, MIS type blue LEDs made by MOBP had already been made by the company people. So I couldn't motivate to write a paper. So my stress was maxed out. Then I got my belief that follow the belief that I have grasped for myself. Or in other words, better not to follow all the people's advice. Why? I am the one doing the most experiments in the world right now. I thought that later I realized my mistake. There are much more amazing people in the US and Europe. But I had a feeling that in the near future I will have a p-type gallium nitride, but there is totally unfounded confidence. Okay. However, in my doctoral course, I did many experiments but could not make p-type gallium nitride, and I thought that there must be something that I do not understand yet. So I learned the courage and persistence not to do something until I found the path to my goal. And then finally, as a result, I was not able to complete my Doctor of Engineering. I had to leave the doctoral course. Okay. However, thanks to Professor Kasaki, I was able to become a research assistant associate at Nanyang University. Then I could continue the research. Then immediately after I became an associate, I was very excited to see the path to my goal. So I found my mistake. I thought that zinc was the best candidate for the impurities, but according to this textbook written by J.C. Phillips, Bonds and Barnes in Semiconductors, the magnesium should be better than zinc in terms of the activation in gallium phosphide. Then I found my mistake. I have to use the magnesium rather than zinc. Then finding a goal of being a first in the world released all my stresses. And then finally I could realize p-type gallium nitride and p-n junction LEDs. With Mr. Kikito, he was the master course student at the time. He grew the crystals. Then I used the electron beam irradiation. So there was no equipment in Nagoya University. Very poor university. So I took 1 hour by small scooter to the collaborator Toyota Gosei, and 7 hours of treatment, and then went back to Nanyang University and characterized it. So it took 9 hours for one sample. But at that time, my motivation was to get the PhD. So 9 hours of experiment is no meaning for us. It's a piece of cake. Then I could get the PhD. But after that, industry players succeeded in made mass production Bro LEDs, leading to the social implementation of full color flat panel displays and general lightings. Okay. So I started the gallium nitride research to develop a new flat panel smart displays, but what I could achieve is only to get my PhD. Then 25 years have passed. Let me explain what had happened in 2014. I was aged 54. The Nobel Prize ceremony always takes place on December 10th. December 10th is the anniversary of Alfred Nobel's death. So about 2 months before, in early October, announcement is held. In 2014, it was October 7th. Okay. And 2 weeks before, we went to the near Mount Fuji for laboratory trip. Please remember this photo. Okay. Yeah, Professor Akasaki, he was very famous. He had been nominated as the candidate of Nobel laureate for more than 10 years. He was also extremely famous. And this person was nameless. So what happened? Every year in early October, many journalists came to Professor Akasaki's or Professor Nakamura's office and waited for the announcement of Professor Akasaki's winning the Nobel Prize. And always, more than 10 years, journalists requested me to give them very nice comments when Professor Akasaki received the prize. So I was, to tell the truth, I was tired of such a situation for more than 10 years. I thought, there is no way Bro LEDs can win the Nobel Prize. So I decided to go abroad without informing to Nagoya University. Then announcement was held during my flight from Nagoya to Frankfurt. Frankfurt was the transit. And there were 1 hour in Frankfurt. So I opened my PC and I found I received a lot of emails entitled congratulations or omedetou gozaimasu in Japanese. But no one wrote me why they were so happy. So I thought I should never have received so many emails. So I realized that, oh, this is what the world calls spam mails. So with fear, I went to the final destination, Lyon Airport. And at the exit, many journalist-like people, Japanese journalist-like people waiting for someone. So I thought, oh, I'm lucky that some famous movie star is coming with the same flight. And then one journalist and the collaborator in France came to me and you received the Nobel Prize. Wow. So the trouble happened in Nagoya University. Mass media entered my laboratory without me. So this is my photo. And I was missing from the press conference at Nagoya University. Okay, that's my Bro LED story. And then I'd like to explain the latest activities in our laboratories. It's a journey to the unknown world. Okay, first is the conductivity control of wide bandgap and ultra wide bandgap materials without impurity, without magnesium, without silicon. Okay. The pioneers of gallium nitride-based high electron mobility transistor was, of course, Professor Asif Khan. And Professor Asif Khan, at that time there was, he belonged to APA Optics, and he requested to Cornell University, led by Professor Eastman, to fabricate the HEMT device in 1993. But as you see in these papers, the Professor Eastman's team could not include as the courses. So Professor Eastman, he was a little bit angry about that. So he requested our team to grow the HEMT structure like this. It seems complicated structure, but for us, it's a piece of cake, because at that time we concentrated on fabricating the blue laser diode. Compared with the blue laser diode, this structure is very, very simple. So we easily grow this structure and send the sample to Professor Eastman's team, and then they succeeded to fabricate the world's best performance HEMT with the highest T and F max. But when I checked the seed carrier density, it was much, much higher than expected, more than 1 order of magnitude. So I imagined that there were some new phenomena. That was the polarization doping, okay? Yeah, this material system, there is a strong polarization, spontaneous polarization and piezoelectric polarization. So the two-dimensional electron gas density is much, much higher than the impurity doping. So it was published by Dr. Ambacher at that time, internship in Cornell University. But this case, the electron density is just concentrated at the interface between the aluminum gallium nitride and the gallium nitride. So the distribution of the electrons is more important. So Dr. Jenner and Dr. Singh, at that time, the University of California, Santa Barbara, developed new ideas of distributed polarization doping by changing the composition of these materials. And then they also succeeded in P-type DPD, distribution polarization doping on N-polar gallium nitride. And then we followed this idea, but in our case, we used not the gallium nitride substrate, but the aluminum nitride substrate. Therefore, the composition control is opposite. By reducing the aluminum composition, we can realize P-type aluminum gallium nitride without magnesium doping. Then succeeded in fabricating the world's shortest wavelength laser diode uh, 271 nanometer without any impurity doping or magnesium doping. And then 3 years later, this case, it was the pulsed operation. But now we are already demonstrating the room temperature continuous wave operation of DPV laser diode. And now, for laser diode case, we use the DPD only for P-type aluminum gallium nitride. But now we can realize both N-type and P-type without silicon or without magnesium. So we succeeded in fabricating the PN diode without impurity doping. Then breakdown electric field is much, much higher than silicon carbide or gallium nitride. Okay. Okay, next journey to the unknown world is realization of carbon neutral society by nitrides. For future energy saving, there are power devices in power supply. So if we use the electricity as the energy source, you have to use the power supply circuits. And in power supply circuit, you have to use the transistors, okay? Now, the silicon transistors efficiency is very high, more than 19% in average. However, 19% is not sufficient, okay? For example, if you operate your PC by using the solar panel on top of your house's roof, you have to use the power exchange from DC to AC, AC to DC, or change the DC voltage. In general, you have to use the 4 times the power converter. So if each system has the efficiency 93%, multiplied by 4 times, the total efficiency is reduced to 75%. So if you change from silicon to silicon carbide or gallium nitride, you can realize 99% of the efficiency. In such a case, if you exchange 4 times, the total efficiency is 96%. That's why we need a much higher efficiency power driving systems. And his student, Professor Jita's students are now doing the research with our teams. Dr. Vipul Sarkar tried to fabricate new diodes. It's called the camel diode. Okay. So one of the expected application of the new system is the electric vehicles. So we think that the role of electric vehicle is movable batteries. Okay. North Carolina State University has a lot of brand. So if you use the solar panel, all the campus, maybe you can charge your electric vehicle at university and then use the charged electricity to your home. The reason is, okay, the problem of solar panel is the solar panel generates too much electricity when in the noon or in summer. So we have to cut the power electricity solar panel from the electricity grids if it generates much higher power. So to solve this problem, the much higher amount of electric vehicles and the charging and discharging system would be necessary. So we are now concentrating on develop possibility of bidirectional charging and discharging systems. The new system would be charging 10 minutes and driving range 1,200 kilometers per one charge, and capacity over 150 kilowatt hours, which correspond to 10 days. 10 days of Japanese household and 5 days of the American household. Okay. So we are now conducting the research under one roof, comprehensive research and development team from crystal growth through the system applications. And Professor Jeter is joining us as the visiting professor and the designated professor. And another one subject is the nitride as the electron source. Maybe many of you know this person, the Professor Robert Nemanichi. He was in North Carolina. Okay, yeah, he conducted research on the electron emitter by nitrides and the diamond. Okay. So nitrides can be used as the electron source. So we established a new venture company, Photoelectron Soul. So we are using the nitride as the photoelectron source. Excite the nitrides by lasers, and then the nitrides emit electrons. So advantage of using the semiconductor photoelectrons photocathode is the efficiency is much, much higher than the conventional metal source. So we are using the negative electron affinity surface on semiconductors. By depositing the cesium, we can lower the vacuum level like this, and then exciting the p-type nitrides, then excited electrons go out. That's the principle of photoelectron emitters. And the advantage of using the nitrides compared with the conventional, for example, gallium arsenide, is the lifetime is much, much longer. It is very, very stable. Okay. So gallium nitride semiconductors solve the low duration problem. And we can use it as the semiconductor inspection equipment for non-logic. Okay, by irradiating electrons there are second electrons. So the material charged to positive. Okay. So if we irradiate whole area, the gate becomes positively charged because of the secondary electrons. Then it becomes on. So source and drain easily connects. But the advantage of using the photoelectron is during this scanning, we can on and off. Easily we can control the on and off by controlling the laser beam. Then, if gate area is not irradiated, this FET becomes off. So we can inspect the NAND logic system very, very easily using our systems. This is the example. This is the 3D NAND logic. And then if we cover the gate area to not to irradiate electrons, the contrast becomes changed. Okay. Then we can easily inspect the NAND logic of each NAND logic. This is one example. And second application is the high aspect ratio imaging using our digital selective beam technologies. Now, the aspect ratio becomes higher and higher, and the depth becomes deeper and deeper. So the problem of checking this performance is if we want to see the very deep area, it was too dark. So if we try to see the deep area, the upper portion is too bright. So we cannot see the deep trench. That was the problem. So using our system, we can easily control the intensity of the electron beam. So we can see the particle at the bottom of the deep trench. So we are conducting the partnership or collaboration with the World Research Partners. It was in 2016 at NC State University. So, you were here, and he is Professor Barriga. Okay. So, finally, the social implementation of the post-silicon semiconductors, especially in our case, three nitrides, gallium nitride and aluminum nitride, our responsibility towards establishing a carbon-neutral society. So, research partnership between North Carolina State University and Nagano University should accelerate the realization of net zero carbon emission world. Thank you so much for your kind attention.
Yeah, thank you, Professor Amano, for sharing your vision on the nitrites, and particularly for sharing your personal journey. I think this is very important for our students.
Yeah.
And so that they remember better, let me recap what they need to do to be successful in PhD. Yeah? to be successful, you need to be dedicated. Yeah?
Yeah.
So maybe you have heard that before. You need to have perseverance and belief, yeah? But before all, you should not talk to old people.
Yes, yes. Yes.
So please, we'll take any questions you might have. Who wants to kick us off? Yeah, Frankie.
Thank you for the very inspiring talk.
Thank you.
I'd like to ask, how was I think we like the rule gallium nitride back in the 80s.
Mhm.
So apparently you did it before Nekema reported it in 1990.
Mhm.
So how was your MOCVD growth different
The MOCVD growth of
gallium nitride?
gallium nitride in 1980s. Yeah, all were challenges. I don't, no, we didn't have the experience of the growing MOCVD, so nor could we use the MOCVD reactors. So we have to establish our own MOVP reactor by running the many journal papers. So maybe today we couldn't accept such challenge because it was too dangerous. But at that time, we could do it. Only following the journal papers.
Any other questions? Yes, Professor Narayan. Maybe you can take the microphone.
Thank you for a very nice talk. When you're trying to grow on these nitrides, on these, there's a problem of relaxing the small strain, where there's a need to have a dislocation nucleation, and that dislocation has to propagate to the interface in a very tough lattice.
Yes.
So that is a challenge.
Yes.
Which, as you improve the device.
Right. Thank you so much. At that time, there was no good single crystal gallium nitride or even aluminum nitride. So we have to use the sapphire as a substrate. So the lattice mismatch is more than 16%. Yeah, the why I use the buffer layer is only by accident. By accident, I could realize the high quality gallium nitride, but still the dislocation density is 10 to the 9th per square centimeter. But the good thing, or we are very lucky that even 10 to the 9th of dislocations, LED efficiently emit light. The efficiency is more than 95% at present. Even we have the dislocation 10 to the 9th. The reason is, well, one of the reasons is the diffusion length of the holes or carriers is very short in nitrides. That's why the effect of the dislocation is not so serious in the nitride LEDs. And also the power HEMT application or high efficiency device applications, it's majority carrier devices. So the effect of the dislocation is not so serious. However, if we try to fabricate much higher power, like silicon carbide, we need to reduce the leakage through the dislocations. So we are now change the material substrate from sapphire to gallium nitride or aluminum nitride. So we are using gallium nitride substrate and aluminum nitride substrate for higher power device applications.
Okay, thank you. There's one more question.
Yeah.
How did you convince
Let-
yourself, as well as your professor, to, your advisor, that it's okay to run the experiment? How did you convince yourself and your advisor that it's okay to run the experiment using the non-working or partially working resistor? And was it more instinct-driven or based on more scientific conclusions you had taken until that point?
Your point is how my mentor advised me, or
I guess, how did you convince your advisor that this was a good experiment to run using a low temperature
Yeah.
aluminum nitride?
yeah.
By not talking to old people.
Yeah, right. Yeah, the good things for me is we can, I could freely do experiments. So it was my mentor's advice not to teach or not to instruct the young student. Young students could freely do the experiments. That's the most important thing. Right?
When you try to grow on gallium nitride, aluminum nitride,
Yeah,
getting gallium aluminum nitride, right?
yeah,
So the lattice parameter is different.
different, yes.
And then there will be strain that generated because of that. How this strain will be treated in your applications?
Yeah, yeah, thank you for that. That's a very important point. Yes, for example, the laser diode applications, the cladding layer thickness would be 0.2 or 0.3 microns. In such a case, we don't need to care about the lattice difference, lattice constant mismatch. However, if we try to fabricate high power devices, we need thicker drift layers. In such a case, we are now facing the very serious problem of the lattice mismatch. Yeah, even though we use the distribution polarization doping technology, the lattice mismatch is very, very serious. So the total thickness is limited. So at present, we cannot fabricate the high voltage devices.
Oh, thank you. Thanks for your many very exciting talk about.
Thank you.
I have a question about the advantages of the power device using gallium nitride, and there are two main advantages. One is the efficiency, and the second one is the size. We can have a smaller
Yeah,
size.
smaller size. Yes, right.
Yeah, can you explain that why can we have a smaller size of device?
Oh, okay. Yeah, that's a very important point. Thank you. We have to compare the channel mobilities of the transistor done by several materials: silicon carbide, and gallium nitride. In case of MOSFET, yeah, we are conducting the MOSFET gallium nitride applications. And in such a case, the channel mobility is most important for high frequency applications. Now, for electric vehicle inverter applications, we need, for example, 100 amps or 300 amps operations. In such a case, the silicon IGBT or silicon MOSFET, the frequency, switching frequency is 100 kilohertz maximum. And for silicon carbide, maybe 1 megahertz would be possible. But using the gallium nitride MOSFET, due to the high channel mobility, we can realize more than 10 megahertz operation. So we can reduce the size depending on the switching frequencies. Okay.
Okay, last question.
I'm just curious, when you were in an undergrad and you said that you went through like 3 years of experiments without success.
Yes.
So how did you come up with like thousands of ideas as an undergrad to run these experiments?
Yeah, thank you. That's a very important point. The reason why I could concentrate is it's amazingly interesting. Yeah, the reason is I had not have such an experience of developing the equipment on my own. That's quite new to me. So that's why I could enjoy, I could concentrate on the experiment. If the equipments have been given by others, maybe I couldn't continue for more than 3 years. The reason why I could concentrate is I could do everything by myself. Okay?
Yeah, so in short, to have a good idea, you have to have many ideas. So that's probably the best piece of advice. So let's thank Professor Amano again for his inspirational talk.
Thank you.
So it was a little bit for everyone, so everyone can take something back home, and I hope you all enjoyed it. Thanks for coming.